This is the video one for classical mechanics. So we have three learning goals for this unit. I want you to be able to solve linear and rotational kinematics problems. I want you to be able to solve force and torque problems. And then finally, I want you to be able to solve work and power problems. So let's get started. For kinematics, we have two broad categories, linear and rotational. So we're going to start with linear. Now, what kinematics is the study of motion. And we're going to primarily focus on 1D, so one-dimensional problems. That's objects moving in a line. We'll take a look at 2D problems like projectile motion, but I won't expect you to do a whole lot of math with that. Now, for motion itself, we have two main types, constant velocity and constant acceleration. So when an object has constant velocity, the object is moving without speeding up or slowing down. A bowling ball is a great example of this. Once you release a bowling ball, it maintains a pretty constant velocity as it travels down the lane. So if I were to make a position versus time graph, what I would see is a nice linear line, because the position is changing evenly with the speed. If I were to make a velocity versus time graph, I would observe a horizontal line because it's constant velocity. And then an acceleration graph, I would have zero acceleration. Generally speaking, the acceleration needs to equal zero for constant velocity. And when we have constant velocity, the way we can calculate things is, as a general rule, just take the distance divided by time. The second type of motion is constant acceleration. And here we have the object's velocity changing. So, this time, if I were to make a velocity versus time graph, the object's velocity is changing, so I would see like a diagonal line. The acceleration graph, if the acceleration is constant, I would see some sort of horizontal line. Now, I haven't forgot about it, but the position graph, that's going to be a little different. At first, since the object is accelerating at first, it's not moving very quickly, so it's not covering very much ground. But as time passes, this object begins moving faster and faster and faster, and that causes it to cover more and more ground. And what that does is it takes the graph and gives it kind of like a parabola-looking curve. So in this one, acceleration is not zero. Acceleration would equal the final velocity minus the initial velocity over time. It's very important for you to understand the difference between acceleration and velocity. So, some kind of questions here. What is the acceleration of an object that's been thrown vertically in the air? Well, once it leaves your hand, it begins to slow down. So that means it's accelerating, it's changing its speed. As it turns out, its acceleration would be negative 10 meters per second for every second. So its velocity changes by 10 meters per second for every second that it's in the air. So if you throw something, let's say you give something a velocity of 20 meters per second. So Once you've thrown it into the air, after 1 second, its speed is dropped to 10 meters per second. After 2 seconds, its velocity has dropped to 0 meters per second. So that's how it's slowing down, by 10 meters per second every second. What is the acceleration of the object at its highest point? Now, if you think about it, it stops at its highest point. The velocity is 0 at its highest point. So many people think, oh, the acceleration must be 0 because it's not moving. That's a misunderstanding. At the very top of the arc, its acceleration is not 0. Its acceleration is still -10. And if we think about it, that should make sense because if you really stop to think about it, just because something is stopped doesn't mean its acceleration is 0. Acceleration is a changing velocity. So if the acceleration were 0 at the very top, then its velocity would never change and it would stay up there, it would hover. And obviously that doesn't happen. Okay, what is the acceleration of the object as it falls back to the ground? Okay, it's speeding up. It's getting faster and faster and faster. So a lot of people think, oh, it must be, 9.8, or I rounded it to 10. So they say, oh, it must be +10. Well, it's actually -10. And that's because the object is getting faster, but it's getting faster in a negative direction. We say down as a negative direction. So, at all points in the object's path, its acceleration stays at a constant -10. Now, for all types of motion, we can use these models here to describe them. These are very, very useful kinematics equations. This last one right here, I write it a little differently. The way I write that last one, I add that x naught over. And really, this right here is probably the most important formula. This one right here, I'd say, is the second most important. This one, if you want to know it, go for it, but you don't have to. But this first one, is the most important. Now, if I have like a constant velocity, the acceleration equals 0. So this equation right here becomes that, and really, if you think about it, that is the same thing as speed equals distance over time. I'll let you think about that, but really that is the same thing as distance divided by time. Okay, projectile motion. This is the study of objects flying through the air. And really the only thing influencing them would be gravity. So for us, we're going to ignore all forms of air resistance. We have to understand that velocity is a vector. It has magnitude, like feet per second, but it also has direction. And we represent the direction with an arrow. So all kind of vectors, like velocity, are arrows. Now, when we have an object, let's say we have an object here, and we're going to throw it. We're going to give it an initial velocity. That initial velocity, let's say it's at some sort of angle, I'll call it theta. Theta could be 10 degrees, it could be 45 degrees, it could be anything you want. What I can do is I can break this velocity up into a y component and an x component. And notice I've made a right triangle. So I can use Sohcahtoa and the Pythagorean theorem to help me, figure things out. So what Sohcahtoa says is sine is opposite over hypotenuse, cosine is adjacent over hypotenuse, and tangent is opposite over adjacent. So we can write out some formulas. So for instance, sine of my angle equals opposite over hypotenuse. So looking here, my opposite is at v naught y, my hypotenuse is v naught. So if I do just a quick little bit of rearranging, if I put a 1 under here and cross multiply, I can find that v naught y is v naught times sine theta. So if v naught were like 100 meters per second and theta were 30 degrees, I could plug those two numbers in there and find out what v naught y would be. Cosine of an angle is adjacent over hypotenuse. So here we see the adjacent is that v naught x, and the hypotenuse once again is the v naught. So again, I can put a 1 and cross multiply. And that gives me a way to calculate what that v naught x would be. Once I have numbers for v naught y and v naught x, I could do a little test. I can use the Pythagorean theorem, a squared plus b squared equals c squared, to see if I get that original v naught back. What this really means is that for all object flying through the air, we can isolate it into an x direction and a y direction. We can look at those directions independently. All right, this down here, trigonometry, this is just a little bit of review. Sohcahtoa. And then also Pythagorean theorem. So for here, I'd have a squared plus b squared equals h squared, the hypotenuse. If I wanted to find just h, I'd have to use a square root, but I can do some things like that. All right, so for projectile motion, the velocity along the x-axis is constant. So if I were to take a look at the acceleration on just the x-axis, it would be 0. The acceleration along the y-axis, however, is non-zero. It is negative 10 meters per second, or negative 32 feet per second. So this would be the acceleration along the y-axis. From here, we can do a bunch of calculations, but the point is to use, not to go into all the theory. So what I provided here are 3 equations that really, especially for a robotics contest, these are really all you would need to know. First off, time of flight. How long will this thing be in the air? That might be something that you need to know. The next one, maximum height. What is the tallest point that this thing will go? Again, that might be something you need to know, especially if you have some, like one year we had this competition where we had to throw objects into a net. It'd be nice to know what the maximum height and everything is. Finally, range. How far will the thing go? That's something else that you may wish to know. And really, those 3 equations, they all come from this one. So, looking at this equation here, on the x-axis, I would say since the acceleration is 0 on the x-axis, that's what we get for the x-axis. And then for the y-axis, we can get that formula right there. So those three equations for time of flight, maximum height, and horizontal range all came from those two equations. All right, this concludes video 1.